The next is motion of center of mass. In motion of center of mass, you're supposed to calculate the velocity of center of mass. You have to calculate the acceleration of center of mass and the force acting over the center of mass. So in motion of center of mass, say this is your system. So this is mass m1. This is mass m2. This is your mass m1. So the velocity of first mass is v1. The position vector of first mass is r1. This is second mass. It's moving with some velocity v2. The position vector of the second mass is r2. This is nth mass. Its velocity is vn. Its position vector is r. And for the entire system, somewhere its center of mass lies. This is the center of mass of the system. This is the center of mass of the system. That's RCM. This is the position of center of mass of the system. So up to last class, we did how to calculate the position of center of mass. Like the last expression that we did is position of center of mass, RCM, can be calculated in this way. This is M1R1 plus M2R2 plus MNRN divided by the total mass of the system. This is the position of center of mass. It's the first equation. Now, if this particle is in motion, then the position of center of mass will change continuously. If particle is in motion, or if system is in motion, then position of each mass will change. So you can calculate the velocity of center of mass. For velocity of center of mass, you can differentiate this entire expression with respect to time. Right? We know that velocity is rate of change of position. So you can write that velocity of center of mass is just rate of change of position of center of mass. This is how we define velocity, that velocity is rate of change of position. So here, instead of a position of a single mass, I'm taking position of the center of mass. So this will be its d over dt of RCM, which is M1R1 plus M2R2 plus MNRN divided by. So the velocity of center of mass is, this m is constant. You can take this m outside the derivative. And if I differentiate this term, then m1 is constant. This will be just m1 dr1 over dt plus m2, it's dr2 over dt. It's up to your n terms, and it will be mn drn over dt. Oh, Sania, so what is dr1 over dt? So what's this term? dr1?
V1.
V1, very good. So it's velocity of first mass. Similarly, this is m2, velocity of second mass.
V2.
And this is mn, velocity of nth mass. So this is the velocity of center of mass. This is equation number 2. Just like velocity of center of mass, Noor, how would you calculate the velocity, the acceleration of center of mass?
I will differentiate VCM again.
Yes. So to get acceleration of center of mass, The acceleration of center of mass is rate of change of velocity, dvcm over dt. So the acceleration of center of mass is simply the rate of change of velocity of center of mass, which is basically it's 1 by m. So this is m1, it's d1 over dt, plus m2, it's dv2 over dt. And you can keep on dividing up to n terms. So that's mn dvn over dt. So the acceleration of center of mass is, it's 1 by m. This dv over dt is the acceleration. So that's m1 a1. Then this is m2 a2. Then this is mn an. This is how we calculate the acceleration of center of mass. Let's call this as equation number 3. You can as well calculate the momentum of center of mass. For momentum, you can use equation number 2, like the velocity, the expression of velocity of center of mass. If I use equation number 2, this is equation number 2, right? This is 1 by m. It's m1 v1. Sanya, do you remember expression of momentum?
V mv ch m1 v1
So that's m1 v1 plus
plus m
v2.
v2 plus m. And
What is m into vcm? This, what is capital M? It's mass of what? Capital M means mass of entire system. So capital M basically means m1 plus m2 up to mn. So you can do one thing. Mass of system. Capital M is mass of entire system. The system for which you are calculating the center of mass. So this m into vcm can be written as the momentum of center of mass. This m1 v1 plus m2 v2 plus mn vn, these are the momentums of individual particles. So you can say that momentum of center of mass is p1 plus p2 up to pn. So if you want to calculate the momentum of center of mass, then just add momentum of individual particles vectorically. The vector sum of momentum of n particles would be the momentum of center of mass. Okay, after this momentum of center of mass, we have one more important topic, that is the concept of force, the force acting on the center of mass. So right now I'm giving you some questions on accelerations and momentum, then we will come to the concept of force. So solve this particular problem. So this mass is moving downwards with an acceleration A. This moving upwards with the same acceleration, but directions are opposite. So if you're taking downwards as positive, then upwards would be negative direction. So you have two, in a system, you have two particles, a particle of mass 5 kg and another particle of mass 10 kg. Calculate. I'm saying this acceleration is A1 and I'm saying this acceleration is A2. This particle is of mass M1, this is of mass M2. Calculate first part. Acceleration of each particle. You need acceleration of each particle, each of the individual particle. Then in the second part, you need acceleration of center of mass. You need acceleration of center of mass. See, first part is very trivial. The acceleration of individual particle is, you can calculate using the concept of this pulley. We did its net unbalanced force divided by the total mass of the system. Once you have A1 and A2, you can calculate the acceleration of center of mass, which is M1A1 plus M2A2 by M1 plus M2. See, for this type of questions on pulley, the formula says acceleration of both the masses is equal. Acceleration is net unbalanced force We did plenty of questions on this concept. We also do this pulley on an inclined plane. This is net unbalanced force divided by total mass. So your net unbalanced force is basically it's 10g minus 5g divided by the total mass of the system, that's 10 plus 5. So 10g minus 5g is 5g over 15. This 5 will cancel this 15, it's 3. So the acceleration is g by 3 now. Now, A1 and A2 depends upon your sign convention. So if I'm saying that downwards is positive and upwards is negative, that means your A2 will be g by 3 plus A, but your A1 would be minus A. It would be minus of g by 3. So that's A2 and A1. You can calculate the acceleration of center of mass as this is m1a1 plus m2a2 but for Sanya, that formula you will use to calculate the acceleration of center of mass. But to calculate the acceleration of individual particle, you will use the concept of pulley.
Okay,
For
sir.
particle, you will use this concept.
Okay.
Where m is nothing but m1 plus m2. Okay, just substitute the values of m1, a1, and a2 and capital M here and get the value of AC, acceleration of center of mass. Note, Fazil, answers. Yuvraj, answer. Okay. So Fazil, your is positive, it's plus 10 by 3.
Sir, which one?
Your answer, it's 10 by 3 is plus 10 by 3.
Yes.
So this plus 10 by 3 means your center of mass is at rest. Is it moving upwards or it's moving downwards?
It's moving downwards, right?
Moving downwards. So if I substitute all values here, then acceleration of center of mass is m1. m1 is 5. a1, which is minus g by 3. m2, which is 10. a2, which is g by 3. Capital M, which is 15. So the acceleration of center of mass comes out to be minus 5g by 3 plus 10g by 3 by 15. So the acceleration of center of mass is 5g by 3 into 15. 3 is a 15. So the acceleration of center of mass is g by 9. So the acceleration of center of mass, g is 10, so it's 10 by 9. So that will be 10 by 9 meter per second square. It's coming out to be positive. It's g by 9, not g by 3. It's g by 9. It's coming out to be positive. That means your center of mass is going downwards. So this is how you can calculate acceleration as well as velocity of center of mass. Okay, now solve this question. You have two particles, a particle of mass 2 kg. It's moving with a velocity of 5 meter per second. Then you have another particle of my 5 kg. It's moving with a velocity of 2 meters per second. Remember, if you are taking this direction as positive, means if you are taking 5 meters per second as positive, then you will take this 2 meters per second as negative. Calculate velocity of center of mass. Capital M, I can write m1 plus m2. See here, m1 is 2 kg, v1 is 5 meters per second. See, it's one-dimensional motion, so I can drop this vector sign here. m2 is 5 kg, but your v2 will be minus 2. It's moving in opposite direction, so this velocity should be negative. It's minus 2. So the velocity of center of mass is 2 into 5 plus it's 5 into minus 2. Yeah, yes, Anya, you're correct. 2 plus 5, so it comes out to be 0. Means if these two bodies are moving with 5 and 2 meter per second velocity, its center of mass will not move. Center of mass will remain at rest. So this example shows that bodies, individual particles are in motion, but center of mass is not moving. Center of mass is at rest. So always remember this thing, that it's possible. It is possible that all particles in a system move but center of mass of the system remains at rest. So from this expression, this statement, you can conclude that some force is acting over the individual mass, which is basically forcing these individual particles to move. But the net force on the center of mass is 0, due to which center of mass is not moving, center of mass is at rest. So it's always possible that individual particles are in motion, but center of mass is at rest. This happens in many problems. We'll come to some real life problems. Okay, so after knowing velocity, displacement, and acceleration of center of mass, the next thing that we need is the force acting on the center of mass, the concept of force. So force on center of mass. Then we will extend this concept of force to conservation of linear momentum. Force on center of mass. So the force acting on the system can be divided into two parts. The force can be external, or the force acting on the system can be internal. Your force could be external as well as internal. Force acting on the system could be external force or it could be internal force. So before starting this force on center of mass or conservation of momentum of center of mass, you should have a very clear-cut division in your mind that the forces that you will encounter may be external or it may be internal forces. So let's differentiate what is external and what is internal force. External force here means force acting on the system by agencies out of the system. So if I give an example, I say that the system is of Earth and Moon. Earth and moon together form a system. So the force which Earth exert on the moon or moon exert on the Earth is internal force, because Earth and moon are the parts of the system. But if sun is exerting some force over Earth, then that force is external. If sun is exerting some force over the moon, then that force is external. So forces applied by the parts of the system or constituents of the system are known as internal forces. But the force applied by the agencies out of the system are external forces. So external force means force applied by agencies out of system. And internal force means force applied by agencies of the system. So to decide whether your force is internal or external, you first have to define your system. Like, what is your system? What are the constituents of your system? If I take an example, I'm taking an example of Earth plus Moon system. I'm taking one system which is Earth plus Moon. Now we have to decide which forces we can consider as external and what forces are internal forces. So force on Earth by Moon. Yes, Fazil, this is internal force or external force? What is your system? Your system is Earth plus Moon. So the force which Earth apply on the Moon or the Moon apply on the Earth are basically the forces by the constituents of the system. So that is external or internal?
Internal.
That's internal. Similarly, force on Moon by Earth. Sania, is it an external force or an internal force?
internal force,
It's internal force. Yuvraj, force on Earth by Sun. Is it an internal or an external force?
Sir, external force.
This is external force. So this force is basically applied by agencies out of the system. So this is how we define whether your force is internal or external. Next, the internal force can change momentum or velocity of individual particles of the system. Due to this internal force, momentum of Earth can change. Velocity of Earth can change due to this internal force. If I'm taking Earth-Moon system as an example, due to this internal force, velocity of Moon can change. Moon can have acceleration due to this internal force. But the center of mass of Earth-Moon system will not move due to internal force. These internal force cannot affect the center of mass of the system. The effect on center of mass of the system is by external force only. So I'm writing this statement. Motion of individual particles of system are not affected by internal force. Are affected by internal forces. So internal forces can affect the motion of individual particle. Like due to this internal force, Earth moves. Due to this internal force, Moon moves. But due to these internal forces, center of mass will not move. But internal forces cannot change or cannot affect motion of center of mass. Cannot affect motion of center of mass. So individual force, internal forces can can affect the motion of individual particles, but not of center of mass. External force can change or can affect motion of center of mass as well as individual particles. We will prove this statement. We will do some real life problems as well as mathematical proof of this statement. But this statement is important for the numericals on conservation of center of mass. First of all, for a numerical, you have to define your system. After defining your system, you will decide the internal and external forces acting on the system. The internal forces can change the momentum of individual particles. When I'm saying it can affect the motion of internal particle of individual particles, that means motion of individual particle can change. The momentum of individual particles can change due to internal forces, but not the motion or the momentum of center of mass. So even in numericals, we will use this concept. If no external force is acting on the system, then individual particles may move, but center of mass will not move. The motion, if center of mass is in motion, then its motion will not change due to the internal forces. So to prove this result, let's say you have a system of m masses, m1, m2, mn. So let's say the position vector of the first mass is r1. The position vector of the second mass is r2. The position vector of the third mass is rn. Okay, do you remember Newton's third law? Action and reaction. Let's say I have two masses. M1 will exert a force F21 on M2. M2 will exert a force F12 on M1. So this F12 is minus of F2. Both the forces are equal and opposite. F12 is minus of F21. If I add them up, then they will cancel out each other. F12 plus F21 will be equal to 0. So due to action and reaction effect, the net force over the system is 0 because individual forces are action and reaction pairs. They just cancel out each other. Is this statement clear? I will use this thing in this calculation just to prove that only external force can affect the system. Is this thing clear?
Yes, sir, it's clear.
And these forces are internal, huh? Because force on M2 by M1 and force on M1 by M2 are not external, they are basically internal forces. So these forces can just cancel out each other. So if I take this system, this is x-axis and I say this is y-axis. You have n masses, M1, M2 and Mn masses. So if I consider this mass M1, then two types of forces are acting on M1. One is internal, which is exerted by M2 or Mn or M3 over M1. And another is external force, which is exerted by agencies out of the system. I'm repeating it again. I'm taking a system of n masses, M1, M2 and Mn. Basically two types of forces. There are two types of forces which are acting over this mass M1. One is internal, which is exerted by M2, M3, M4, as well as Mn. Another is external, which is exerted by the agencies out of the system. Similarly, on M2, two types of forces are acting on M2. One is external, another is internal. Similarly, if you take any of the mass, then you will observe that two types of forces are acting on it. One is internal by the parts of the system, another is external, agencies out of the system. If I use the expression of acceleration of center of mass, using acceleration of center of mass, means acceleration, this was the expression, the acceleration m1a1 plus m2a2 plus mn am divided by, you can multiply this m with this ACM, mass m with the acceleration of center of masses m1a1 m2a2 plus mn am. This is mass of the system multiplied by the acceleration of the center of mass of the system. So see, this is M1A1. M1A1 means force acting on the mass M1. This is force acting on the mass M1. This is force acting on the mass M2. This is force acting on the mass M2. Now you have to decide, this M1A1 will depend only on internal force, or it will depend only on external force, or it will depend on both internal plus external. Tell me. Okay, just read that statement, the statement that I wrote in the previous slide. In the first line, I wrote that internal force can change or can affect the motion of individual particle, right? If you read that statement again, you will see that the first line says that internal force can affect the motion of individual particles. So if you read first line, then your answer could be this, internal, A. But if you read the last line, that external force can change the motion of center of mass as well as the motion of individual particle, then you will come to this conclusion. So the first line says that internal force can change the motion of individual particle. Last line says that external force can change the motion of individual particle. So actually it's internal plus external which can affect the motion of individual particles. Okay, now tell me, if I say this is MACM, this is acceleration of center of mass, then which option will be correct? Only internal, that's option A. This acceleration will depend on only external, that's option B. Or this acceleration of center of mass will depend on external plus internal, that's option C. Which option is correct? What's the first line of the statement that I wrote in the previous slide?
Motion of individual particles of a system are affected by internal force,
Then,
but internal force cannot affect motion of center of
so
mass.
does the acceleration of center of mass depends upon internal force?
No,
So is it possible that A is correct?
no.
So A wrong. Next, okay, read the next line.
Internal force can affect motion of center of mass as well as individual particle.
So okay, so acceleration of center of mass will depend upon external force, right?
Yes.
But not on internal force. So A and C
Yes.
cannot be correct.
External B is correct.
B is correct. So always remember that statement. That statement, you will need that statement in conceptual questions as well as in numericals. So let's prove that this ACM will depend only on external force. As we have discussed, that motion of individual particle will depend upon external as well as internal force. So that I write, this is F1 external force on first particle, plus F1 internal, which is internal force on first particle. Similarly, for M2A2, I can write this as, this is F2 external force on second particle plus F2 internal force on second particle. And this is Fn external plus Fn internal. So this is external and these are internal forces. Now see, as we see in the system of two masses, that internal forces cancel out each other. Internal forces can cancel out each other because they're action-reaction pairs. So I can write that F1 internal plus F2 internal plus Fn internal is equal to 0. The sum of all internal forces is 0. F1 internal plus F2 internal up to Fn internal is 0. They will cancel out each other. Net internal force on the system is 0. But external force will not cancel. So F1 external, F2 external, Fn external will be the total external force on the system. This is total external force on system. Total external force on the system. So if I substitute all values here, what I will get that mass into acceleration of center of mass is F external because all internal forces is 0. So what we have written in that statement, that acceleration of center of mass will depend only over external force, that thing we have proved. That acceleration of center of mass depends only on external force, not on the internal force. Okay, let's solve some numericals based on this concept. So in these numericals, you basically have to decide, is some external forces acting on the system or not? The whole thing depends upon external and internal force. For that, first of all, you have to decide your system. This is a river bank. And just near this river bank, a plank is floating. The length of the plank is L, some L. A plank of length L is, this is river, the plank of length L is floating on it. The mass of the plank is capital M. And this is man. The mass of man is small m. This is it. The man is at rest. The plank is floating just near the bank of the river. This is the bank of the river. Now, can you guess what will happen if this man start moving towards the bank? What will happen with the plank? It will stay at this position only or it starts moving?
It will move backwards.
Will move.
Move backwards, right? The man starts walking on the plank So if this man starts moving towards the bank, then this plank will move backwards. Let's say the plank moves here. So you have to decide when this man reached this end, how much distance this plank cover. So first of all, decide what is your system. In this question, first of all, decide what is your system. Your system is man plus plank. That is your system. Okay, if I divide this problem into parts, then the first part is to calculate center of mass of the system. Calculate position of center of mass of system. See the bank, this is the bank x equal to 0. Take origin at bank. Solve the first part. Calculate position of center of mass of the system. I'm dividing this problem into 3 steps. That's the first step. System means man plus plank. The length of the plank is L. The mass of the man is M. You can consider your man as a point mass. So it's not the point, you're not calculating the center of mass of just the rod. You're calculating the center of mass of rod plus man. You can consider man as a point mass. This is how we calculate the position of center of mass, m1x1 plus m2x2, isn't it?
Yes, sir.
Yes.
Here m1 is man, so I call this m1 as small m. Sania, what is x1? Let's check how much is x1. The separation of man from the bank of the river.
L.
X1 is it, very good. Fazil, I'm taking m2 as m. What should be x2? Where is the plank?
Sir, 0.
Why 0? Why not this point for plank? Plank is a point mass or a rigid body?
Rigid one.
So what we do for the rigid body, we will first replace rigid body by its center of mass. If you remember, in the last class, we did question on 3 spheres.
Yes.
I told you to calculate the center of mass of the system. What was the first step? You first replace each sphere by their respective center of mass, isn't it?
Yes.
Then we calculated the center of mass, all 3 center of masses. Just like sphere, in the case of rod is not a point mass. I will first replace rod by the center of mass, C1. So this C1 is not the center of mass of system. This C1 is center of mass of plank only.
So C1 will be equal to L by 2.
Yeah, C1 will be equal to L by 2, right? C1 is L by 2. So this C1 is basically representing the entire plank. So X2 is L by 2. Is it clear?
Yes.
Yes, sir.
Okay. Now I need center of mass of not just the plank and the mass man M. So somewhat here, the center of mass of the system will lie. This blue is the center of mass of system. Which system? Man plus plank. So you can replace this man and plank by this point. Now I need the x coordinate of this point. I need x coordinate of this point, which I call x center of mass. Substitute these values, get the value of xcm. That's the first part. If I'm breaking this numerical into parts, that's the first part. So this is your xcm, right?
Yes.
Okay, let's move on to the next part. When this man reached this end, this another end, I again need the center of mass of the entire system. I need the position of center of mass of the entire system when this man have reached the other end of the plank. When man reach the other end of plank, then coordinates of center of mass So what are the coordinates of center of mass now? When this man have reached the other end. Let's call this as M1. Mass will not change, but the coordinates will change. M2, X2 prime. Then I need M1 plus M2. As earlier, this is XCM prime. So this is the position of center of mass when man is at this end. Now this is the position of center of mass when man is at this end. Small m is m. Sania, how much is x1 here? Or it should be x. See, x coordinate simply means the separation of man from the bank. Huh? So this man is at a separation x from the bank. So x1 is x1, right?
Yes.
Noor, this is x1
Yes,
prime.
sir.
M2 is capital M. How much is x2 prime? See, the center of mass of Planck is somewhat here. I call this as, this is C1, the center of Planck, center of mass of Planck. How much is x2 prime? What's the x coordinate of this point? Is it L by 2 or something else?
L by 2 minus x.
Minus x. See, this is origin, this is C1, this is x2 prime. This is x and this much is L by 2.
So then L by 2 plus x.
Yeah. This is origin and this is the center of mass of the rod. If this distance is L by 2, then from the origin this will be L by 2 plus x.
Yes, sir.
Yes, sir.
So if I substitute all these values here, then the x coordinate of center of mass, m1 is m, x1 is x, m2 is capital M, x2 is L by 2 plus x over m plus m. That's the second step for this problem. Okay, now tell me, when this man starts walking on the plan, when man walks the involving forces are internal or external? When this man is walking on the plank, the force exerted by man on the plank is internal or external?
Internal.
Internal, yes, because your system is man plus plank. The force which man exert on the plank is internal. Forces involved are internal. Sania, another question. Listen very carefully. So the forces involved here are internal forces. And this is the center of mass of the system, right?
Yes.
This T1 is the center of mass of Planck, but I'm talking about the center of mass of the system, man plus this Planck system. And the coordinates of the center of mass is earlier, this is XCM. When the man is at this end. When the man comes at this end, then the XCM is this thing. Tell me one thing. If the involved forces are internal, then does the motion of center of mass will change? So when the man is at this end, then center of mass is moving or at rest?
Be at rest.
It will be at, see, this is at rest. This is Planck. This man is standing of the plank. If man and Planck are in motion, are at rest, that means center of mass is at rest. Center of mass is at rest, not moving, right?
Oh, yeah.
And you're saying that internal forces cannot affect the motion of center of mass. That means
Yes.
even when this man reached the other end of the rod, the position of center of mass of the system will not change. Right?
Yeah. Yes.
Because internal forces cannot shift center of mass. It cannot change the position of center of mass. It cannot affect center of mass. Since forces involved are only internal, so the center of mass will not shift anywhere. It will remain as it is, where it was earlier.
Yes.
So you can write this thing as x position of center of mass is equal to x prime c. You can just equate 1 and 2 and get the value of x, right? If it is not moving, that means the position of center of mass that we calculated from first equation is same as that of position of center of mass that we calculated using second equation. So they should be same. Now equate them and get the value of x. How much is x? See, this is ml plus ml by 2 by n plus m. You don't have maths, huh? Sania, you don't have math.
Yes,
But you had maths in class 10th or not?
I had.
You had. Then you should not make mistakes even in addition and subtraction at least. See, this will get cancelled out. This is ml plus ml by 2. You'd always double check your calculation. It's mx. Just multiply it here. Okay. So that's ml by 2 plus mx. So cancel this thing with this thing. Okay. Small m and capital M are two different things. You're mixing small m and capital. This is ml. You can take x as common. This is small m plus capital M. You can't write this as 2m. Small m and capital M are different masses. So that's ml by m plus m. So the distance through which this plank will move is this ml by m plus m. Is it clear? Okay, the next topic is conservation of momentum of center of mass. The next is conservation of momentum of center of mass. So the momentum of center of masses is the vector sum of momentum of individual particles. So that's P1 plus P2 up to P. So if you keep on adding the momentum of individual particles, then that vector sum of momentum of all particles will be the momentum of center of mass. So external force acting on the system, external force on system, F external is d over dt of momentum of center of mass. So if I take an isolated system, an isolated system means a system where external force does not act. So system for which F external is 0 is isolated system. If I take an isolated system, then rate of change of momentum of center of mass is 0. If I say that rate of change of momentum of center of mass is 0, that means TCM is constant. So this is the conservation of momentum of center of mass. That means if you have a system which is isolated, a system on which no external force is acting, then the momentum of the center of mass of the system will remain constant. Its momentum will not change. This is the conservation of center of mass. But for conservation, this is an essential condition. Momentum of center of mass will not be conserved unless the external force on the system is 0. Now see some applications, real life applications of this principle. So application of conservation of momentum of center of mass. So the first application is, say if you have a molecule of mass m, which is at rest. The molecule is at rest, that means the center of mass, initially the momentum of center of mass is 0. If this molecule break due to some internal forces, molecule break into two parts, due to internal force. So initial momentum is 0. So can you guess the final momentum of the molecule?
0.
0.
0.
Momentum will not change because no external force is acting on the molecule, so momentum should remain same. But this breaks into two parts. One part of M1, another part M2. So what will happen? These two parts will start moving in opposite directions, exactly opposite directions with equal and opposite momentum. Like P1 is equal to minus of P2, which means P1, if I take it to the left hand side, plus P2 equal to 0. And this is the final momentum of the system. So if a molecule breaks into two parts due to internal forces, then the two parts will move in opposite direction, exactly opposite direction with the same momentum, so that the final momentum of the center of mass remains conserved. This is again the principle of conservation of center. Is it clear?
Yes, sir.
Yes,
If
sir.
it breaks into two parts, then they will move in opposite direction. But if it breaks into n parts, then those n parts can move in any direction. They will move in a way that if you add the final momentum of individual particle, it will add up to 0. Because external force is not acting on the system, so its momentum should remain conserved. Let's again break this question into parts. So you have a car, the mass of the car is m, and on the car you have a child of mass small m. So let's consider this as a car. The mass of car is capital M, and this is child on the car, its mass is small m. Initially this is the initial system when both child and the car are at rest. Fazil, what is the initial momentum of the system?
0.
Yeah, the initial momentum of the center of mass would be 0. So, Sania, this car is placed on a frictionless surface. There is no friction between the car and the ground.
Okay.
This child jumps in the forward direction with some velocity. What should happen with the car? Car will remain at rest when the child jumps, or something will happen with car?
Car will remain at rest.
Car will remain at rest. See,
There
what
is no.
happens when you jump from this car and there is no friction, then this car will move in opposite direction. This happens in a boat. If you have ever observed this thing, if a boat is floating on water, if you jump from the boat, then that boat will move in the opposite direction. Not just boat. If you have say, if you have a board or a wooden plank, you're standing on the plank. If you jump in the forward direction, then that plank will move in the backward direction.
Okay.
So this car is moving in the backward direction with a velocity v. The mass of the child is m, the mass of the car is m, velocity is vcm. So what's the final momentum of the system?
VCM.
Final momentum of the system. Momentum is mass into velocity. The momentum of the child, which is mu,
MU.
minus momentum of the
Minus.
car minus. Why minus? Why not plus?
Because
Opposite
it's moving
direction.
backward direction.
It's moving in opposite direction. This is 1, this is 2. Okay, now check this question and tell me, is there any external force acting on the system? Just read the entire statement and see. Is there any information about the external force acting on the system?
No. Yes. No.
Yeah, the system consists of only man and child, and the child jumps, only the force exerted by the child on the car is internal, no external force. If there is no external force, so can I say that momentum remains conserved?
Yes.
Initial momentum of center of mass will be equal to final momentum of center of mass. Use this equality and get the value of V, velocity of car. I need velocity of car now. So if I equate them, then initial momentum is 0, final is mu minus mvc. So mvc is mu now, so vc comes out to be mu. Fine.
Yes, sir.
So based on conservation of momentum, you can get this type of questions. Okay, so this completes translational motion of a rigid body. So for translational motion, we studied the concept of center of mass. The next thing is rotational motion of rigid body. So can I erase it?
Yes, sir.
So let's recall everything. We started this translational motion with the concept of center of mass. We first calculated the position of center of mass of two particle system, n particle system, and then a rigid body. Then we calculated the motion of center of mass, the velocity of center of mass, the acceleration, the concept of force, that only external force can change the motion of center of mass. Internal forces cannot change the motion of center of mass. Then we did conservation of momentum of center of mass. Okay, one last question on conservation of center of mass. Say I throw this ball in air in this path, in this projectile path. This ball is following this, or let's say let's call this bomb. This is a bomb. The bomb is following this projectile path. This is the center of mass of the bomb. This is C, this is C, this is C, this is C. This is the center of mass of the bomb. It's following the projectile path. If this bomb explode, will the center of mass follow the same path or its path will change? This is before explosion. This is the path followed by center of mass. Path followed by center of mass. What will happen after explosion? After explosion, will center of mass follows the same path or it will deviate?
The center of mass will continue on the same path.
Yes, because during explosion, the forces involved are not external, they are internal forces. So the center of mass, the path of center of mass will not change. It will continue to move in the same path. Although individual particles will move, they will move in different directions. Because once the bomb explodes, the particle keeps on moving in different directions, but not the center of mass.